All right, we're recording now. So for x in the set of all real numbers and non-negative integers x, the rising factorial function that's what we're defining. I use the notation x to the n with an overbar for x to the n rising. We can read this as x to the n rising is the product, and it has a factorial-like behavior. We have x to the n rising equals x times x plus 1 times x plus 2, and so on until we have x plus n minus 1. So there are n factors here. And so for those of you that have done linear algebra, these guys will form a basis for the polynomial space. For those of you who just remember earlier, we already defined x to the n falling as x times x minus 1 times x minus 2, and so on, down to x minus n plus 1 in the same way. And if x is itself an integer, if x is an integer, let me make it a non-negative integer, then this is then x to the n falling equals x factorial over n factorial, and x to the n rising equals x plus n minus 1 factorial divided by x minus 1 factorial. Now that guy looks familiar, right? This is p of x and n, or no, not quite. It's that's hold on. This isn't right. It's not over n factorial. It's over n minus x minus n factorial. There. Now it's p of x and n. And this is right because I based it off of the actual product there. So we have some identities that connect these. We have x to the n rising is equal to x plus n minus 1 to the n falling. And you can see that because if I just reorganize these terms here, x plus n minus 1, and then minus 2, and then minus 3, and then finally minus n, well, here, let's just write it out. So x plus n minus 1 to the n falling is x plus n minus 1 times x plus n minus 2 times x plus n minus 3, and so on. And then the last couple of terms here, we need, or not terms, factors. So the last one, in the first one we subtracted 1, so in the last one we will subtract n, so this will be x plus n minus n, and in the one before it we'll subtract x plus n. We'll subtract n minus 1. So this one is just x, and this is x minus 1. Sorry, x plus 1. And so this would be, now think of this as x plus n minus 3, and so on all the way up till we get to x plus n minus 1. And that is all of the terms we have here. So that is just a shift. And in fact, x to the n rising is related to choosing with replacement in the same way that just x to the n falling is related to choosing without replacement. We'll get there in a second. The other identity, this is called the negation identity, or sometimes the upper negation identity, although that has a little bit n 0. Yes. Is there a place? This one? Oh, n, yeah. Yeah, that should be n and n 0. So x to the n falling equals -1 times, I'm sorry, I said it backwards. These are both true. X to the n rising, or the one that's written is x to the n rising equals -1, -1 to the n, negative x to the n falling. So this is the one that's written in the notes. This is also going to be true. You can just replace x with -x. So to show this one, let's see, which side should we take? Let's take the right-hand side first. Or you know what, let's just take -x to the n falling and write that out. So that is -x times -x minus 1 times -x minus 2, and so on until we get -x minus n plus 1. Remember, there are n factors here. So if I take out a -1 to the n, then that is x times x plus 1 times x plus 2, and so on, times x plus n minus 1. That is -1 to the n times x to the n rising. And of course, you can put the -1 to the n on either side of that equality. So that negation identity is just, it's of particular importance to me. I've used it for a lot of different proofs in my work, and it's amazing to me how often being able to shift between these is handy. All right, let's talk about the binomial coefficient. So we've talked about this a lot because I love it. No other good reason. I mean, it is kind of awesome and it's everywhere, which is part of why I love it. But we will define u choose n to be equal to u to the n falling over n factorial. And now what's different about this from before is that u can be any real number and n just has to be a non-negative integer. So we still have some restrictions on the lower number, but the upper number does not have to be an integer, or even it originally had to be a positive integer, right? Or a non-negative integer anyway. And so this is our definition. this is the real beauty of the falling factorial function, is instead of defining it in terms of just regular factorials, which only work for integers, we can define it for other numbers, for any real number. Now, the next example is to find a Maclaurin series. For f of x equals 1 plus x to the u, where u is not necessarily an integer. And I just want to point out that using the u in both places is supposed to be a clue. So remember, Maclaurin series is the series, the sum as n goes from 0 to infinity of fn at 0 times x to the n over n factorial. We're at 0 instead of a. That's the difference between Taylor and Maclaurin series. So these are centered at 0, which is just a nice place to center this guy. So that's the nth derivative. So what are our derivatives here? F prime of x equals u times 1 plus x to the u minus 1. And if I plug in 0, then I just get u. And f double prime of x equals u times u minus 1 times 1 plus x to the u minus 1. When I plug in x equals 0, that's u times u minus 1, which is u to the 2 falling. And f triple prime of x is u times, oh, that should be a u minus 2. U minus 1 times u minus 2 times 1 plus x to the u minus 3. Plugging in x equals 0 will give me u to the 3 falling. And in general, the nth derivative of f at 0, I'm just going to skip to it, is going to be u to the n falling. So the Maclaurin series for 1 plus x to the u is equal to the sum as n goes from 0 to infinity of our derivatives are u to the n falling, x to the n over n factorial. But we were trying to find, so as a Maclaurin series, that's the way we would write it. Oh, back down to the bottom of the page. The nth derivative of f at 0 is u to the n falling. Just same reason as before. We're going to get u times u minus 1 until you get u minus n plus 1 times 1 plus x to the u minus n. But then 1 plus x, when you plug in 0, is just 1. So 1 to anything here, we're going to define to be 1. So as a Maclaurin series, that's written well. This is f, the nth derivative of f at 0. This is x to the n over n factorial. But notice that we can write this as a generating function by just shifting that factorial over. So that's u choose n, x to the n. This is the generalized binomial theorem, or Newton's extension of the binomial theorem. And there is a limitation here. We need x in magnitude to be less than 1. Technically, we don't even need x to be real here, but we're in a combinatorics class, so let's keep it real, shall we? So this works for any complex number x with magnitude less than 1, and it's just the extension of the binomial formula. We get the same binomial coefficient, well, not the same, it's the extended binomial coefficient. But that means that we can expand things like 1 plus x to the minus 1. Now, technically, we could already do this because we had a generating function for 1 over 1 plus x, right? But we can use the binomial theorem in order to quickly get our coefficients. So this is equal to the sum as n goes from 0 to infinity of minus 1, choose n, x to the n. Now, what is minus 1 to the n? Well, here's where it might be useful to remember what 1 over 1 plus x look like. 1 over 1 plus x is the ordinary generating function for which sequence? For the sequence where we have 1, negative 1, 1, negative 1, 1, negative 1. I sure hope that's right. I just did that off the top of my head. Anybody back me up? Give me a thumbs up in the chat or something. No. Anybody tell me if I'm wrong? Okay, thanks, Alex. Yeah, right, because 1 over 1 minus x is just all ones, and so when we negate the x, it just puts a negative sign on the odd coefficients. So that means that negative 1 to the choose n equals 1 if n is even, and negative 1 if n is odd. That's 2 divides n and 2 does not divide n is the notation I'm using there. Just n is even, n is odd. What about 1 plus x to the negative 2? So that's just negative 2, choose n times x to the n, summed as n goes from 0 to infinity. Well, what would that look like? Let's do this one the other way. Let's calculate this one using the formula. So negative 2, choose 0 is 1. That's just always the case here with x to the 0 falling is 1 because it's like a factorial. And then negative 2, choose 1 is equal to negative 2 times, just negative 2 over 1 factorial, which is negative 2. Negative 2, choose 2 is negative 2 times negative 3 over 2 factorial. That is equal to positive 3. And negative 2, choose 3 is negative 2 times negative 3 times negative 4 over 3 factorial. That's going to be negative 4. And I think you can see how our sign is going to be decided based on whether n is even or odd, right? Because we're going to have 3 factors for when n is 3, and we'll have 2 factors when n was 2. But then everything except the last factor in the numerator is going to cancel, and perhaps the sign with the denominator. So we have -2 choose n is equal to -1 to the n times n. Sorry, not times n plus 1. Now, and I'll try not to lose that, but I got to write something else. So what if we had done it the other way? What if we had looked at this as 1 over 1 plus x quantity squared? Well, 1 over 1 minus x quantity squared, sorry, is the ordinary generating function for the sequence 1, 2, 3, and so on, or just the sequence n plus 1. And so when we negate the x, we get the negative sign on the odd one. So 1 over 1 plus x squared is the ordinary generating function for the sequence -1 to the n plus 1. So far, we haven't done anything we couldn't have done before using our using generating functions for these reciprocal powers. Don't want to lose focus. Looked like it was going to wig out for a second. So what can we say in general? How about 1 over 1 plus x to the p, or 1 plus x to the -p? Well, we can write that as the sum of -p choose n, x to the n, as n goes from 0 to infinity. But keeping in mind that 1 over 1 plus x to the p is 1 over 1 minus -x to the p, we also know that this is equal to the sum, as n goes from 0 to infinity, of -p plus n minus 1 choose n, -x to the n. I maybe skipped a step there. What am I claiming for real? Really, I'm just claiming 1 over 1 minus x to the p is equal to the sum as n goes from 0 to infinity of -p plus n minus 1 choose n, x to the n. And then from there, getting to this by just negating the x. So where does this come from? Well, this comes from two places. This comes from the fact that this is the coefficient, this sequence is the number of ways to place n indistinguishable balls into p distinguishable cells, allowing empties, and that its generating function was equal to 1 plus x squared, and so on, to the p, which was equal to this. And we did that last time before, maybe both. We kind of keep coming back to that generating function. It's a p. And so if I start with this, and then I negate my x, I get 1 over 1 plus x to the p equals the sum as n goes from 0 to infinity of -p plus n minus 1 choose n, -x to the n, which is the sum of -1 to the n negative p plus n minus 1 to the n times x to the n as n goes from 0 to infinity. And now this sequence and this sequence have the same generating function. And that means they have to be equal. And that's what's called a generating function argument. They get used quite a bit when we're dealing with sequences. So we can claim two sequences are equal if they have the same generating function. And that's just because of the three-way equality. So this gives us our upper negation identity for the binomial coefficient. So if I have negative p choose n, this is equal to negative 1 to the n, p plus n minus 1 choose n. And that's not always the way it's written, just because why would it be? That's the way it happens to correspond with this generating function argument that we just gave. But I could just as easily say, well, if I have p plus n and I want to negate the upper index, that's what it's sometimes called as, then this would be n minus p minus 1. Choose n. It's sometimes written that way. Now, this this requires something. And now I have that this is true if p is a natural number only. That's a positive integer. I'm trying to recall, there is an issue with the upper negation identity as it pertains to its region of truthiness. And I can't quite recall if there's any reason why this can't just be any integer. I think the upper negation identity is true for, you know what? Hang on. I'm going to pause for a second from the recording. Sorry, let me quickly repeat that because I forgot I had stopped recording. So I'm going to challenge you guys, anybody who's watching now or later, to prove the upper negation identity using the negation identity between the rising and falling factorial and the fact that p plus n minus 1 choose n is p to the n rising over n factorial. You also may need that p to the n falling is p choose n is p to the n falling over n factorial. Back to our regularly scheduled stuff. Actually, no, I think that's a good place to stop now that I say that. I've been rambling on for quite long enough, and I'm a couple of examples shy of where I thought I would end, but I want to leave time for questions. All right, anybody have anything? All right, well then, I'm gonna let you guys go. Have a good one, everybody.